Yeah, we start the recording. Well, last time we are talking about scheduling, right? We talk about what is context switching. Okay, context switching basically is if you don't look into the details, basically means a task switch from one job to another. And I didn't constrain my discussion over one CPU or three CPU or single core or multi-core. Basically, if you have multiple cores, you can think of, oh, there is a big queue. Okay? If you have go to which kind of restaurant is using this model? KFC is using this model. Okay? KFC has one queue and multiple CPU are there. Right? You join into a single queue and go to one of the CPU, you get a resource, right? Get the service. So basically, if you have multiple cores or multiple CPU, that is the scenario. Or park and shop. Park and shop is the same. Single queue, multiple CPU. Right? I mean, those ladies are the CPU. Okay. Yeah. Later, I will always use that description. Make sure that you have go to park and shop. Okay. Now we will have a first kind of scheduler. Okay. That scheduler is fantastic. How fantastic it is. I guess it is one of your model in doing assignment. So what is that? We call this a batch processing system. One of our very old retired professors, okay, he teach me one hardware course, okay, and you know, usually the length that the time that they use for telling story is proportional to their age, okay. So I hear many stories at that time. And one of the stories is about ITSC at 1970s or 1960s. Okay, we already have ITSC, but that time we don't call it ITSC. The name is called CSC, Computer Service Center. Computer Service Center, yeah, CSC, right? Okay, so it's just collide with our names. Okay, don't care about this. The CSC or the ITSC is basically serving the entire school because there are too few computers in the CHK, and they use this scheduling. So what is this scheduling? I don't know whether you have pay to wash your clothes in Hong Kong. Okay, not the one you find in the dormitory, not the one in dormitory. The one that we call laundry service. And how can you get the service? Basically, you bring a bag of dirty clothes, okay, and submit the job. Okay, I call it submit the job. Submit the job to the shopkeeper. Okay, and the shopkeeper, what will the shopkeeper do? Okay, the shopkeeper won't clean the job. Okay, I mean clean the job. Okay? Won't do anything over the job. But tell you one thing, an estimation of time that the dirty clothes will be cleaned. The estimation. Okay, usually he or she will tell you, I come back tomorrow. Okay, or come back at the same day at a specific time. Okay. So very powerful. Actually, they are human scheduler in his brain. Okay, he can schedule. Okay, whether it will finish within today or tomorrow. Okay, then what were they doing? They actually do things in a batch. Okay, they collect the clothes. Okay, I don't know whether this is true or not. Okay, but I think it's horrible. Okay, think about it. Collect all clothes and clean together. And it means that your clothes and my clothes clean together. How can they distinguish? Okay, so usually I don't think this is the case, but for time being, I want to discuss over what is a batch system. A batch system means that I have A job, I have B job, C job, D job. Okay, all jobs first of all cannot be mixed together, right? Just like the laundry case. If your clothes make my clothes, how do you distinguish that? So we have a job A. Okay, it's my clothes. And while I'm cleaning, maybe your clothes is under other treatment, okay? Or my clothes finished washing, then I will go to the dryer to make it dry. So your clothes can use the washer, okay? And so basically, in this kind of system, we have a scheduler. Okay, scheduler, this guy is a scheduler, and the scheduler will control the pods in the system. I don't know how many pods, okay, how many CPU, I don't know. How many are maybe, even the printer, okay, is a shared resource, right? After you complete a job, if you print out, Okay, so maybe you have to also schedule printing tasks. Okay, then you have the results. This kind of computing system, okay, usually have a very close look at one factor. And what is the factor? We call it turnaround time. Okay, I have told you just now, the shopkeeper of the laundry service, they will have a very accurate, maybe it's their, how can I say? Maybe because they have a certain time that they will do something, okay? Then they can estimate when your job will finish, okay? And we call the time between you submit the job and you can collect the job, the earliest time you can collect the job, we call it turnaround time. Okay? This kind of system emphasizes turnaround time. So back in our 1970s times in CSCI, so how this system works, according to that professor, okay, the professor is called Professor Moon, already retired, he told us that there is a guy, a system admin, okay, will collect a job. So according to another professor tell me that what are their jobs? They call it punch cards. I never seen this, okay? I'm too young, okay? So punch card, so their job is submit the punch card, and the output is a printout, okay? A paper about the answer that you have computed and finished on the job. Now, the system admin will try to submit the job, and what is the meaning of minimize your turnaround time? Usually, turnaround time is, first of all, the time that you ask for the CPU resource. Okay, at that time we're very poor. Okay, we have maybe a few computers. So you have to tell the system that my job approximately will run for 5 hours. Okay, say for example. Now, think about it now. I ask you to write a program and you tell me how long it will run. Usually you will fail this kind of estimation, right? It's already quite complicated. So our system admin won't do this. Okay, you say that you need 5 hours. So they allocate 5 hours to you, and whether you can collect it 5 hours, what I have to mean. Okay, whether you can collect it 5 hours later, usually not, because you have a scale resource, limited resource. So you will take more time. So the turnaround time does not equal to the time that you run on the CPU. Usually you have to wait. Okay, so later on we will tell you another concept called waiting time. Okay, waiting time and turnaround time are different. Turnaround time is the job is submit, and then you wait for 3 hours, then you will collect the job, finish items. Okay. So what are the goals or what are the properties? Okay. First of all, I already tell you about turnaround time is a primary goal. We want to minimize it. Okay. Minimize means that it's not to minimize your CPU requirement. I cannot improve your program and make it shorter. Okay, so what I can do is to make a perfect schedule so that I can minimize it. Okay, of course, if we want to minimize it, usually the next goal I've already derived goal will we have a very efficiently using all components in a parallel manner. Okay, parallelly. Okay, I have a printer. Okay, while the printer is printing, okay, we don't need the CPU attention, so CPU please go to run another job. Okay, and then we have another derived goal called high throughput. High throughput means that okay, I have maybe only one machine. Can I finish 10 jobs within the day? Okay, or within the day I do a measurement. Okay, 10 will be a good throughput, 6 will be a bad throughput, so on and so forth. Okay, so there is another analogy. Okay, the analogy is back in ENGG 1010. Yeah, the elevator system. Right? In the elevator system. Now I'm not telling you to remember how to write the code. Okay, but imagine that you are waiting your elevator in SHB. Okay, now we look at it from a system point of view because you already experienced that. How to design a system. So if you think about it in the SHB elevator, what is the meaning of high throughput? If it's high throughput, it means that, I collect your requests, so many people press button, The high throughput means that I can deliver as many people as possible within the limited time, right? But not guarantee your happiness. Yeah, not guarantee your happiness. You can be very awfully inconvenienced, right? You have to wait from the 10th floor. I have to wait for 3 rounds of an elevator skipping me, okay? And then you are trying to deliver people because only one guy here unhappy, but other guys are happy. Okay, then you are maximizing the throughput. Another way is, can the system minimize my waiting time? Okay, it try their best to, when you press a button, I guarantee that you will be sent to your destination within a certain time. Then it's not guaranteeing the throughput, right? You already written the elevator system, you already know that. If you try to minimize a particular guy waiting time, it's not means you have a high throughput. Okay? So later on we will keep on mentioning these concepts. Understand what I mean? Okay. Oh, by the way, not all people here have written that elevator system. Okay. Basically, that elevator system sucks. Okay. I write it. I know how to write it. I know. Okay. Yeah. So this sucks. Okay. So basically, if you don't know about it, you didn't do anything. Okay. So another platform is nowadays platform. Nowadays platform. It's not the batch system. Not a batch system. It is what we call an interactive system. So interactive system mentions 2 things. One is whether can it give you a reasonable time to wait for response? So what is the meaning of reasonable? What is the meaning of reasonable? I love this example. This example is perfect. Just perfect. PlayStation. Yeah. When you play PlayStation, when it enters the stage that it will try to load something, okay, and it's expected to be a long time. So what will you see from the screen? Loading, right? Basically, you are under the control of that screen. That screen controls your emotion, right? And think about it. If while you're playing the games, all the loading screens are skipped, but give you a black screen. Think about it. What will happen? Yeah, you will smash your controller, you will smash your TVs, okay, or shake your PlayStation. What happened? Okay, right? So basically, your emotion is being controlled. Yeah, or I don't say that it's controlling your emotion, but give you some expectation. When you see the loading, you expect you can go to have a bath. Okay, oh no, bath is too long. Go to restaurant, I don't know what you want to do. Okay, yeah, you can take a break. Okay, pick a drink. Okay, so there is something that we call a reasonable response time. It depends on what is advanced, and this kind of design is perfect, just perfect. It tells you this is long or this is short. Okay, I don't know whether you play PlayStation or not. PlayStation 3, okay, maybe it's too fast, so the loading time will show loading and suddenly it's finished. Okay, I'll bet in my time I'm playing other kinds of system. The loading appears. Okay, I can go to washroom and come back. Still loading. Okay, so this is what we call a response time. Of course, another is meeting your expectations. Right, I already show you that while it's loading, it's expected to be slow. Okay, so this 2 factor, and together, what is the meaning of interactive system? Interactive system means that I give you inputs. I expect you to finish that. Not finish, but give me response. Okay, in a certain reasonable time. Whether this is finished or not, we don't know. We don't know. Okay, so if you can remember that, I don't know, for Windows case, okay, for Mac case, okay, when I click on a button launching Excel, say for example, I need to wait, okay, and I know that the computer is working because I saw the beach ball, I saw that the icon pop is moving, okay. Yeah, this is called response. Okay, and one more, I cannot find any real system to entertain you guys. Okay, so later on when we talk about this kind of scheduler, I can only make up of some, unrealistic system. Okay, what is a real system here is flight control system. Okay, it should be an OS. Okay, usually we call it industry OS. Okay, or nuclear reactor, right? So what is this kind of system? This kind of system is designed, first of all, to listen to many sensors, okay? Say for flights, many kind of sensors, okay? I don't know what are the sensors, maybe radar, maybe other kinds of things, okay? Reactor, maybe temperature, or a number of neurons that is coming, okay? Or a number of radiation level, okay? Then what are the core of this kind of system design? The core is whether you can predict, okay? Or maybe predict, maybe it is about that kind of system. There's a physical model, okay? So we cannot do anything over it, but here we can do something over it, the deadlines. So what is meeting deadlines? It is not about your assignments. It means a piece of data is coming from a sensor, and it carries a deadline, right? Maybe the sensor is a flight control system that a few minutes later you will hit the mountain. Yeah, you're so close to a mountain. Okay, so there's a warning coming, and it carries a deadline. If you don't process it later than 2 minutes, okay, then it will be another dangerous alarm coming. Okay, so it will bear some deadlines over this kind of real-time system. Because real-time system is not mean real system. Real-time system needs to sense many things, and everything have a time there. We have to handle it as fast as possible. Okay, or it will become useless. Now we will talk about different kind of scheduling algorithms. Most of the algorithms you are already using. Okay, I don't know whether you are aware or not. Okay, so first of all, let's define what, when we talk about algorithms, first of all, we will talk about the algorithm goals, what are the inputs, what are the outputs, right? Now, what is the algorithm inputs of a scheduling algorithm? It's a set of tasks, right? I don't know how many tasks we have. Why I say I don't know, okay? It depends on whether this is a, what we call offline scheduling algorithm, or offline scheduling platform, or an online scheduling platform. So what is online, what is offline? Offline means that I know that from time 0 to time 10, I will collect so many tasks, okay? And then within this time, after I collect all things, I will ignore all things later and do the schedule, okay? So I won't respond to later job submission, okay? So it's called offline. So that means that we can make the perfect schedule for offline system. And how about online? Online is your elevator system. Yeah, or the current real elevator system. You will receive requests at any time. And when you receive this request, you have to respond to it. Okay, so we call it online system. And usually online system cannot be if you want to solve it, okay, and what is the difficulty? The difficulty is this kind of online scheduling system, we call it NP hard. How many of you know what is NP? Yeah, you should have heard of it. Yeah, should have. Means, yeah. Not you don't have a polynomial time algorithm to solve this class of problem. Okay? So this NP hard. If it's online. If it's offline, it's polynomial time. Okay, you can solve it perfectly. Find the perfect schedule. If it is offline. Okay? So basically, that means that our algorithm, no matter this is Mac or Windows or Linux, okay, if we talk about scheduling, always online. So basically, all the algorithms that we are going to teach you, tell you, are approximating the best results. We are not guaranteeing the best results. And of course, for each task, we have some inputs, right? Each task, of course, if in real system, what is the program that you are trying to run? What is IO stream, something like that, but we will ignore them. Okay, we will only take care about the arrival time. Okay, when it's submitted to the system. Okay, whether the system will respond to it, it depends on the algorithm. But I want the time. And this is something nonsense. CPU requirement. Okay, so what is the meaning of CPU requirement? Say I want to, when I submit a job there, okay, I need a 2 CPU unit time. Okay, then it will finish running. Okay, now for the sake of our discussion, we need this matrix. Okay, there's a denominations matrix, okay, I mean, these values, okay? But basically, we don't have this value in real system, okay? I don't know how many of you is taking fluent visual. No, should be 1 or 2, at least 1 or 2, huh? No? Oh, Andre will answer that. It is a Hawking problem. How many of you heard of Hawking problem? Only you. Oh my God, he's a non-major student. Okay, basically, okay, I reduce the problem in a sense that, okay, every junior programmer will understand. Okay, so what is the measurement of a CPU utilization or CPU requirement? Basically, it's before you run the program, you know how many times you need it. Is it possible? Is it possible? So this is a very classical logical thinking. Basically, you cannot. Okay, the proof is you cannot. I mean the result. The proof I will show you. Okay, I give you a general idea. Say, if there exists a program that we always know that when it will stop. Okay, when it will stop. Okay. Say for example, we have this kind of program, and basically, can we write a program to detect another program has stopped or not? If we can always know that a program will stop or not. If I have a program A, I don't know for how many times it runs, but I just claim that I can always measure it. I know this before it's run. So basically, we can use another program to measure that. And basically, there's a big contradiction. If you know that this program will stop, okay, for how many times? And another program measures, basically we don't know whether that program will stop measuring it, right? Or I would say that how many times you need to measure a program whether the program will stop or not. Basically, we cannot estimate that relationship, okay? Or yeah, later on I send you on YouTube. Okay, there's a very good YouTube talk about the Hawking problem. Okay, yeah. Or you attend Fluent 3.0 next year. Okay, I mean next year. Okay, I mean not retaking. Okay, so yeah, yeah. This Hawking problem is a very fundamental concept that if someone tells you that this is a real scenario, that guy, okay, you can skip his lesson. Okay. Basically, we cannot. We cannot. And here, that means that all slides later are all, a false claim. Okay, just a simulation. Okay, but this simulation can guide you to design of a scheduler. Okay. And what is the output? The output is easy, but I always have some things that we have to take care of. First of all, the turnaround time appears again. Okay, when we design a scheduler or we do a simulation over the scheduler performance, okay, we usually take care of 2 guys. One, when you submit a job, when this job ends. I already said that, say the job needs 5 hours. You may not be able to finish the job within 5 hours because there are other jobs. Okay, so it will be bigger than the CPU requirement. And other things is called waiting time. So what is the waiting time? Waiting time is something easy to understand. Okay, the thing is in park and shop. Yeah, I don't know how many of you is staying living in a dormitory. Okay, if you're living in dorm, you have to visit our park and shop to buy things. Now the bad things come when you go to park and shop at around 7:00 p.m. Disaster. Huh? Disaster. Now, put yourself into that scenario. Okay, someone is smiling. That means that you know the scenario. The scenario is like this. While you are in the queue, you are very unhappy. Yeah, who tell me he is happy? Okay, come on. Yeah, I have to do some analysis over your mind. Okay, so usually you won't be happy to join the queue. Okay, and while you are approaching to the cashier, okay, you are still unhappy. But while you are being served, you become very happy, right? No matter how long it takes, right? If you reach the cashier say that, oh, I need to do something but related to your task, of course. Okay, do something related to your task. It may take 15 minutes. You won't complain. You will happier than while you're in the queue, right? So the time that you are in the unhappy state is the waiting time. The time that you are in a happy state, okay, is the time that you enjoy the CPU resource. So it is not shown here. So basically, is turnaround time is the waiting time, okay, plus the time that you are being served. Okay. So basically, we have three components. One is a serving time, one is waiting time, and the two guys add together will be the turnaround time. Okay. So if you don't understand, okay, tonight, 7 o'clock, go to parking shop. Remember, buy as many things as possible. Then you will know what will happen. Okay? Other things are the outputs like the scheduling order. We need to know who will finish first, who will finish next. And then what happened next is, number of content switching. We already covered that content switching may be expensive. So we want to minimize it. Okay? But in a parking shop case, you won't entertain what is minimizing the number of content switching. So later on, we will talk about other kind of scaling system. We will talk about it. This guy, okay, we'll talk about all things. Now, let's go. We have basically 1, 2, 3, 4, 5 class of scheduling. Okay, basically we are in this hybrid state for every modern operating system, no matter Windows, Linux, Mac. Okay, we are all in this system. Okay, so that means other system, maybe it's just old system, maybe something imaginary which doesn't exist, which only stay in the simulation level and no one try to implement it. Okay, first of all is first in, first out. Okay, and what's first in, first out is the parking shop case. Okay, next is start first, which is imaginary. What is the meaning of imaginary? Shortest job first. It means the shortest CPU consumption. I already tell you that this is just a piece of bullshit. You cannot estimate the time. So that means this is an imaginary system. But it happens in real case, real life. Okay? Is your deadline scheduling algorithm. Basically, you don't schedule deadline, right? You schedule short job first. You try to finish, say, there is a written assignment and also there is a program assignment. You will try to finish the written assignment first. But you usually wrongly estimate the CPU resource that is needed. Basically, that written may have the same length as a programming assignment, but you wrongly estimate it. Okay, this is your job. Okay. Next is round robin. Round robins very seldom appear in real life, but always happen in computer. It means I execute this job for a very short moment of time, and another job. Okay, say I have 5 tasks, A, B, C, D, E. So I will execute A, B, C, D, E, and then go back, A, B, C, D, E, go back, A, B, C, D, E. To give you an illusion that every task is running in parallel. Okay, of course, if we have multiple CPU or multiple cores, that round robin will be giving you a higher throughput or the shorter turnaround time. Okay, priority scheduling. Priority scheduling and priority multiple queue scheduling has a slight difference. First of all, priority means that every job has a different priority class. What is the meaning of multiple queues? Means in every priority class, you can have different implementations. Okay, we can have a priority class 5 levels, and all 5 levels using the same scheduling, no problem. Then it will be the basic priority scheduling. If we have a 5 priority scheduling class, all 5 have different treatments. Okay, then it will be multiple queues. Okay, and all current systems are using this. Usually the highest level will be first in, first out. The lowest level will be round robin. Okay, of course that round robin is not simple round robin, it's weighted. How many times left? Good. So we can at least finish up to short job first. Okay, so what is this diagram? This diagram usually is, I would say that very easy, and that's why usually it will appear in final exam. Yeah, easy, then final exam will appear that. Now, let's look at the algorithm input. Basically, this algorithm is first in, first out. First in, first out is park and shop case. When you first join the queue, you will be served earlier. Okay? And what is here? Here is the arrival time. Okay? I just come up with some random numbers. Okay? You don't try to ask, okay, why this is 0, why is 1, why is 2. I just come up with some random numbers in this example. And the CPU requirements, okay, I usually love to explain this case not using the park and shop, but using KFC. Okay, why? This CPU requirement 24 is actually who buys the buckets. I hate those guys who buy buckets. Yeah, I just need a cup of soft drinks, okay? I need to wait for you for 24 seconds, or no, in real case it's not 24 seconds, it's longer. Okay, so this is the schedule output. You can see this, wow, if before me is the guy buying the buckets and it is FIFO, then this guy will take the CPU and won't leave. Won't leave, right? He is very happy, he's enjoying the service. Okay, but you are waiting for his termination and you want to terminate him, okay? Because you're unhappy. And then you will receive this. So little CPU, but you ask for it, right? You want just 3 units, okay? So also the P3, also 3 units. And then we can derive some numbers. Why we derive the numbers? Because we can compare the effect, okay? So what's the effect later on, I'll tell you. So the waiting time, I guess no one will argue with me whether I'm doing a correct job or not. 0, this guy enjoying when it's birth, okay, no one is waiting, so we'll enjoy the CPU resource, no need to waste, no unhappiness feeling, okay, wow, good. And for how about this guy birth at second number 1, maybe time unit number 1, and while it is waiting, okay, this guy is enjoying, so for how long? It's 23 time units, okay, so that's so and so forth. You can calculate the average waiting time, and also the average turnaround time. Turnaround time is the difference between the time you enter the system and the time you leave the system. Okay? Now, what is the next example? Next example is, I don't know, there's a godlike person, okay? Know that this P1 is a KFC bucket lover, okay? We love to penalize those guys. Okay, those guys take long jobs, so make other people unhappy. You can see this, the P2 and P3, okay, it's very unhappy. So how about I make a perfect schedule like this? Yeah, but of course I have to adjust the arrival time. Okay, so that's why I said there is a godlike person, okay, to change the world. Change the world, this P3, okay, comes earlier than P1. Okay, so basically it's P3 and P1 swap their arrival time. And look at the figures. Look at the figures. The average waiting time is just 2. So the aggregate unhappiness effect is minimized, right? This guy only unhappy for very few amount of time. But previous case, okay, if you don't eat KFC, okay, go back to Sharkin or whatever places, okay, ask your friend to buy a bucket and you stand behind it. Then you will experience how unhappy you are, okay, in this case. Okay, or park and shop, okay, waits for a person who have free cars. Okay? I see some professors do this. I'm not picking those free cars. Those professors, okay, they have a big family. I don't know how many members, but they have free cars. Okay, and so happened that I stand behind them. Oh my God. Okay. So there is a godlike person to reschedule it. Okay. So basically, why people ask for the next kind of scheduling system? Because we basically have such a need, and this is a sorted job first. Basically, it's a sorted job first, a scheduling algorithm. And maybe you can think about it in your real life, okay? While you have 10 is too much. Okay, 5 assignments, okay, packed together. Okay? Basically, you will ignore the deadline, okay? Because if you say the programming assignment deadline is tomorrow, okay, but you estimate you need 2 days, basically you will give up, okay? And try to do something that which can be finished within 1 hour, okay? So this is solve first. Okay, so some very short summary. Just recap what I said. Okay, this is not good, but this happens every day. Happen every day. If you want to understand the theoretical part of a FIFO, there is a course. I can't remember the course code. It says IERG 4020 or 4, and this is a 4,000 level IERG called Curing theory. Curing theory. The Curing theory is just to measure FIFO systems, okay? But they measure different kind of arrival pattern, or whether it's a Gaussian distribution or a geometric distribution, or what kind of distribution you can name, okay? To do the estimation, what is the average queue length, okay? What is the average waiting time, so on and so forth, okay? If you want to understand FIFO systems, there is a theoretical course about it, okay? I can't remember what's the number. Okay, once I take it, I got C+. Yeah, really. It requires some pyro course that I didn't take. So basically, I'm taking 2 courses together. Okay, so solve first, which is easy. How easy it is? Basically, we can pre-schedule. Okay, we look at the schedule at the current moment. Then I pick the source job, schedule it, and until it finishes, I won't schedule other tasks. Okay? Or you can have a second choice. Second choice is that this happens a lot, okay, which is real. You are running a specific job, say you are doing my OS course phase 2. Okay? You know phase 2 takes many hours. Okay? Some people complain to me some years before, I need 2 weeks to finish it, okay? Yeah, but don't get it wrong, it won't be finished within 2 weeks. Okay, if you think in that way. Okay? Then it's a long job, but it's the only job, so you schedule it. And suddenly, I don't know which class, maybe your UG. Okay, your UG class has a very short assignments, very small assignment. Only take 2 hours. What should you do? Don't do OS, right? Do the UG assignment. Okay? Right? Do the UG assignment, and usually wrong estimation, you take 1 day. Okay? Then you finish it, and then you switch back to OS course assignment. Okay? We have a name for the just now the example. The example we call it preemptive scheduling, right? You remember it? Preemptive means that I will stop a job if I want to. Okay? And that's why SJF software has 2 categories. One is a non-preemptive, one is preemptive. I know which kind you love it, okay, but we can have some objective measurements. I think the time is not enough for me to finish it, okay, but they are just animations, okay. Next week, we still have Thursday's lecture. I forgot about it, okay. We have Thursday lecture, okay, and from Thursday, okay, only 5 or 10 minutes we will finish that, okay, and we will try to speed up a bit. Speed up a bit, that means that we have around 60 pages of slides. And I guess we can finish it, the entire part on Thursday. And then we will go to the last part 5 of this chapter 2. Okay? So that's it.